Okay, here we are on day 1 looking at the locker problem, and I apologize that this one took a little bit of time to get it up here because I had to redo the locker problem video. I'm having to redo the locker problem video because it was a little bit weird in the online thing. So here we go. Here's the printout that will be on your D2L. You may want to print it yourself. If you don't want to print it yourself, you don't have to. You could just read it and then work on it yourself. So I'm going to use a manipulative for this that's called a 2-color counter. And it comes out, it's yellow on one side, red on the other side. If you don't have 2-color counters, you don't need 2-color counters. You can use pieces of paper and put X's on one side and leave the other side blank, or you could make your own somehow out of construction paper and tape together yellow on one side, red on the other, if you want it to be exactly like mine. But they don't have to be. You can do any old thing to make your own, right? And to make it okay. So here we go. This is what it says. In Washington Middle School, there are 1,000 students and 1,000 lockers. All of the lockers are shut and unlocked. Each year for homecoming, the students line up in alphabetical order and perform this following strange homecoming ritual. The first student goes down and opens every locker. Okay, goes through and opens every locker. The second student goes to every other locker and closes it. So they go to 2 and close it. They close number 4. They close number 6. They close number 8. Okay, so that's the second person. The third student changes the state. So that's an interesting phraseology. We'll talk about it in a second. The third student changes the state of every third locker, beginning with locker number 3. Okay, so and it says if the locker is open, the student closes it. If the locker is closed, the student opens it. So we'll talk about that. And continues, the fourth person does that to the 4th locker, the 5th person to all the 5th lockers, and so on and so forth until the 1,000th person changes the state of the 1,000th locker. Okay. So we're going to talk about what that looks like for us in the locker problem. So I'm going to use my handy dandy 2-color counters. I'm going to turn them all up yellow. You can turn them all up red. It does not matter as long as you know what things stand for and you go from there. So in a second, I'll make myself a little note on what's what. Okay. So I'm going to let's do 20 lockers. 20 lockers sounds good. No? Yeah, 20 lockers sounds pretty good to me. Okay. And I'm lining mine up in rows of 5s, but they don't have to be rows of 5s. I just think that the 5s will be easy for me to keep up with. So, I think 20 is a nice big number. That's not 1,000. I don't want to deal with 1,000. I'm going to make y'all deal with 1,000. I'm going to use this strategy. If you've taken our middle school or our elementary math classes 1350 and 1351, you should know that there are some strategies out there that are like this one's work a simpler problem, right? Work a smaller problem, however you want to think of that. So we're going to try to utilize some of those strategies in this course. So instead of doing 1,000 lockers, I'm going to do 20 lockers, which will be nicer for me, right? Okay, so if I can see a pattern going on with 20 lockers, then I will be happy. All right, and I'm going to be, just for the sake of laziness purpose, I'm going to say that all of the lockers were red originally, and that the first student has already gone through and opened every locker. So for my purposes, yellow is going to be open. And red is going to be closed. Okay, so in other words, I should have started them all out red and then flipped them all over because that was student number 1, but I don't want to do that because I put them out there. So I'm just going to say yellow is open, student number 1 has already gone through, they're all open, and then we'll talk about what happens with all the others. So what happens with student number 2? Student number 2 goes through and closes them all, right? Well, closes every other locker. So student number 2 closes number 2, number 4, number 6, number 8, number 10, 12's going to close, 14's going to close, 16's going to close, 18's going to close, and 20's going to close. So, you know, if I was looking, I could see this every other one, yellow, red, yellow, red. So that means that I did it right in my pattern. I can see that, and that the evens are all closed, basically, right? Okay. So now let's talk about that change the state thing. I'm going to give you a second right now to think about it. Think about locker number 3, which is a multiple of 3, right? So, and then it says they start with number 3 and go every third one. So that'll be 3 and 6 and 9 and 12 and 15 and 18. So think about those. Think about the state of those lockers and changing the state. So to me, hopefully you took a second and thought about it. And at any point when you're doing these videos, if you want to, you can pause it and then think about it, work on it, whatever, and then come back and listen to me go more in depth. So that's fine. Okay, so number 3 is currently open. I'm going to close it. Number 6 is closed. I'm going to open it. So what I think about whenever I think about 3s here is that multiples of 3s could be odd, like 9. 9 is open. I'm going to close it. Or they could be even, like 12, which is closed, and I'm going to open it. Okay? So that's what they mean by change the state. So they don't want to have to say if it's open, close it, if it's closed, open it. So there's number 15. I'm going to close it. 16, 17, 18. I'm going to open it. And we know if we had 1,000 lockers here, 1,000 colored tiles or 2 color counters that represent all those lovely lockers. If I had 1,000 of them, 21 would be, I would change its state, and 24 and so on. But I think that 20 is more than enough for us to see a pattern here. Okay, so that was person number 3. So now what? Number 4 needs to change all the states of all their lockers, right? So number 4, person number 4 is going to walk down and go 1, 2, 3, 4. I'm going to change this one. And then they're going to say 5, 6, 7, 8. I'm going to change that one. 9, 10, 11, 12. I'm going to change that one. Oops. Come on, you. Change. 13, 14, 15, 16. I'm going to change that one. 17, 18, 19, 20. I'm going to change that one. So that was number 4. Okay. Then what? Number 5. Number 5 is going to change. These will be easy. Number 5 and number 10 and number 15 and number 20. Good job, number 5. You're done. Okay. Everybody can count by 5s. He likes that, so he's happy he was number 5 this year. Okay, so then what? Number 6 goes through, right? So who does he change? Think about it. He changes 6, and he changes 12. And if you're not sure where those fall, you can count them out. It's fine. And there's one more, 18, right? Okay. 6 is done? Yeah, 6 is done. Okay, so then what? 7, right? 7 changes his 7th locker. But he also needs to change number 14, right? So 10, here's 14. Oh, come on, 14. Doesn't want to work with me here. All right, so 7's done. He would have changed 21, but it's not big enough, or there aren't enough 2 color counters. Okay, 7's done. All right, 7's done. Then what? 8. 8 changes 8 and 16, right? So 5, 10, 15, 16. You see why I lined them up in 5s now. It's a little teacher hint. I can count by 5s really easily. If I had enough space, I would have done 10s probably, but okay, so who did I just do? 8. 16's done. Now 9. What about 9? 9's going to flip, and 18 again, right? Okay. All right. Then what? 10's going to flip, and 10 flips. Number 10 flips locker 10 and 20. And then something interesting happens because I'm out of numbers that can double, right? So 10 could double to be 20, but the next guy is number 11, and his double would be 22, right? And that's off my grid. So I only have to flip the 1, right? So 11 flips, 12 flips. Come on, 12. These guys are too flat. They don't want to flip over for me. 13's going to flip. 14's going to flip. 15's going to flip. So all of those are going red all of a sudden. That's interesting. 16 was red, so he's going to flip to yellow. And then 17 is going to turn into red. 18 is going to turn into red. It's kind of interesting because I end up with a whole lot of reds. Okay. And only 4 yellows, which is good because that's what I wanted. Okay. So I go and I look at it and I say, okay, red was closed. So all these red guys are closed, but I have a few conspicuous lockers that are standing open, okay? So which ones are open? Well, that's 1, 4. Which one is this? 9, and 5, 10, 15, 16, right? And hopefully those numbers mean something to us. We look at those and we go, oh, those are a special set of numbers, so think about that for just a second. What do we have there? Those are all perfect squares, right? Meaning that they're all some number times itself to get me that. 1 times 1 gives me 1. 2 times 2 gives me 4. 3 times 3 gives me 9. 4 times 4 gives me 16. And if I continued with the perfect squares pattern, we know the next one would be 5 times 5 gives me 25, right? So I didn't have a big enough grid for that, but if I had, then I'd know that the next one that would be yellow would be number 25 down here. Okay, so we see a really cool pattern going on here. That's nice. I always like it when I see a pattern. And then the question asks you for the paper asks you for some different questions. It doesn't ask you this question, so I want to talk for just a second about number 1. Number 1 is a special kind of number. And the reason why number 1 is special, think about what we did. The first kid, it was closed, and the first kid opened it, right? That locker. And then think about it. Did anybody else touch that locker? So when kid number 2 came out and went to closing lockers, did he touch that one? Did he close it? No, he skipped it and he went to number 2 and number 4 and number 6. So the second guy didn't touch it, right? What about the third guy? No, the third guy just went to number 3 and the fourth guy just went to number 4. So the only person who touched this particular locker was the first kid that went through. Okay, so this locker has been standing open the whole time. Now, locker number 4, he's not so special, right? That locker, because it was opened by number 1, closed by number 2, opened by number 4. Okay, what about 9? Is he as special as 1? No, because he was opened by 1, closed by 3, opened by 9. Okay, so he was touched by 3 different students. Both of those were. Okay, and before you think, oh, it's three students touched it, let's talk about 16 down here because he was special. If you didn't notice, I flipped 16 a number of times, so let's think about it. He was opened by number 1, closed by number 2, opened by number 4, closed by number 8, and then opened by number 16. So 1, 2, 4, 8, and 16. He had 5 people touch him. So he's not as special as number 1. Number 1 only gets touched once. So even though the paper doesn't mention number 1, I want you to think about the fact that the number 1 is in its own little category. Even though it is a perfect square, we know that. It is in its own category because he's the only one that got touched just once. He's a special guy. And if you start thinking about different words that you've heard, different vocabulary from your background, there is a there are some interesting words that are about to come out when we start talking about different number theory stuff here. But number 1 doesn't always fall in all the categories. So just think about that. Okay, so in your homework, I'm not going to go really in depth about anything. I did point out to you that these are perfect squares. And normally in class, I would have made you go home and think about it and then come back and tell me they were perfect squares, but we don't have enough time for that. But what I am going to do is I'm going to make you think a little bit beyond perfect squares. So I want you to think about, what does it mean to be a perfect square? Okay, so mathematically speaking, not just the word perfect squares, but mathematically thinking, what does it mean to be a perfect square? So you're really going to have to think about some words like factors and multiples, and I don't know, maybe the word prime or composite might pop in somewhere. So we're going to see some stuff happening in the next week or so, and I'm not going to come back and redo this. So first of all, read chapter 1 because it's going to help you with this, and second of all, really think about, what does it mean to be a perfect square, because that's going to help you with your homework. So your homework is, after doing this, pretty easy. So a little 16-minute video, and you should have it. How many lockers will be open? How many lockers will be closed? So we just said the open ones are the perfect squares, right? So what your job should be to figure that out is figure out how many perfect squares are there that are less than 1,000, or I should say 1,000 or less, right? So how many perfect squares are there between 1 and 1,000? And then all the rest of them will be closed, right? So we don't have to figure out that number. We should focus in on the special guys, which are the ones that are standing open. They're the perfect squares, okay? All the rest of them are going to be closed. Which lockers will be open and why? So they want to know the actual numbers. So you're going to have to think about which numbers are perfect squares. It seems like, oh my gosh, this is going to take me forever. But just think about it. I've only got 4 of them here, and I'm already through 20. Okay, in fact, we already had the 5th one. We mentioned it a second ago, or I mentioned it a second ago, 25, and there were only 5 of them. So it's not going to take you long to get really big numbers out of this, okay, and it won't take you long to go through 1,000. Which lockers are open and why? Well, we already know why. It's the perfect square thing, but if you can give me a little more mathy reason than just they're a perfect square, that would be good. Which lockers will be switched the most times? That's a number theory question, so you're going to have to think about what's going on behind there. I talked about this one only was touched once. This one was switched 3 times, 5 times. Is it just going to keep on going up? Is it going to be 7, 22, 49? I don't know. Well, I do know, but I want you to think about it and know. And think about what determines whether it's a 1 or a 3 or a 22. Who knows? So I want you guys to know which ones are switched the most times and why. That's a mathy reason. It has something to do with the makeup of those numbers. And then last but not least, how many lockers and which ones will be switched exactly twice? So you're going to have to think about, once you have your answer to all these things, if you're thinking in the right mathy way, it should help you to think, oh, I know why they're only switched twice. So that'll give you hopefully a little hint and think about where you're headed. Okay, so that's the video on the locker problem, and I hope that that visual helps you. If you want to make a bigger grid and keep going and figure out what does 40 look like, what does 100 look like, you can do that. I hope that I've given you enough. I feel like what I've just told you is enough for you to solve the locker problem and to finish that assignment, so that you're not having to make 1,000 squares, because that would be really stinky of me. So don't do that. I don't think you need to do that. Hopefully this answers your questions. All right, good luck with the homework. If you have questions, let me know. Yay!